Statistical analysis question here, which states that computers from a particular company are found to last on average for 3 years without any hardware malfunction with a standard deviation of 2 months. At least what percent of these computers last between 31 and 41 months? Well, we have to look at what we have and what the question is asking for. The question is essentially asking what is the probability that any computer chosen at random from the computers that this company makes will last between 31 and 41 months. So immediately we know that we are attempting to model some random variable. Let's call it large X. And based on the fact, number one, that we're given the average and the standard deviation only, as well as the fact that a company is assumed to produce more than 30 computers per year, we'll talk a little bit more about this 30 figure in a later video, right? But based on the fact that we're given the average and the standard deviation, we can assume that we are meant to model this random variable x given the normal distribution, which of course takes the mean and the square of our standard deviation, otherwise called our variance. So the model for this particular question would look something like this, where 3 years is 36 months, of course, with a standard deviation of 2 squared. So 2 squaring that to get the variance is 4. So we'd have something like this, right? Which would look a little bit like this, where the normal distribution, of course, is bell shape and symmetrical. Let's pretend that was symmetrical with the mean in the middle. 30, I'm sorry, this will go to 40, right, on this side, and let's say we're going to 32 on this side. So essentially, underneath the normal distribution, what we're seeing is the entire probability, or the entire sum of probabilities, which of course is going to be equal to 1. What we're attempting to find here is what the area is between these 2 points only, which is the point of 31 months and the point of 41 months, which seems like a pretty simple, definite integration until you look at the equation which the normal distribution is given by. It is quite a, I can't use the word complex, but it's quite a difficult integral to evaluate. However, long ago, someone evaluated a great deal of these integrals, but the catch is they evaluated it for a normal distribution, which looks something like this, which we'll call the standard normal distribution. It's shaped exactly the same, except we have a mean of 0 and a variance of 1. So it would look like this. We call this a standard normal distribution. So in order to take advantage of those values which they've computed and put into what we call the z table, we have to now be able to standardize our normal distribution here into this form down here. How do we do that? We do that using this equation here, which is our random variable x minus the mean over the standard deviation gives us this value z, which is what we call the standard normal distribution variable, right? The relevance of this to us is that we can plug this z value into a table which will return for us phi of small z, which is simply the probability that this big Z is less than a given small z, right? So for any given value along here, let's say this is small z here, we'll be able to figure out what is the probability that the value we've put in is smaller than this. Or in other words, what is the area of everything to the left here? You can see how this would be of some use to us. So let's go ahead and get started with that. So for our z, the first value that we're going to want to look at is our 41 months. So that's 41 as our random variable minus our mean, which of course is 36, all divided by our standard deviation, which is 2. Let's call this z subscript 41, and then let's look at z subscript 31, which is going to be equal to 31 minus 36 all upon 2. This is going to be equal to 5 over 2, and this is going to be equal to negative 5 over 2. Negatives are quite interesting in the normal distribution because it's symmetrical. So whatever we have over here, let's call this value z. If we have a negative z here, the areas here are both equal. So this makes it quite easy for us. And you'll see on the z table when I do bring it up that there actually are no negative values. Okay, so where do we go from here? We have to find 5 over 2 on the z table. Before that, let's convert this to a decimal form since there are no fractions on the table. This should be 2.5. So we're looking for 2.5 on the z table. Let me actually bring the z table up right now. The z table is here. We're looking for 2.5. So let me just crop out the relevant portion of the table so we can kind of see how it works. All right. So here's a small portion of the z table, right? We're looking for, as I said, we'll be getting back phi of z out of the table, right? So we're looking for the value 2.5. Here it is. It's right here. It's a nice round value. And we can see the value of the integral between 0, well, not 0 actually, between the leftmost bound and 2.5 is 0.99379, right? So let's say that phi of 2.5 is equal to 0.99379. Perfect. All right. So what does this look like for us? Looking at it again on our normal distribution, what we've found so far, assuming that this point up here is 41 months, what we've found so far is the area of everything behind this 41 months, all the way back, which is half of the work because now we need to go ahead and find the value. We need to go ahead and subtract as well the value here at 31 months. But as I said before, because this is symmetrical, all we need to do now is find the area of right here and subtract it from what we have in total, as it's the same as the area right here. So the area for right here, given that the overall area is 1, and the area of this section from here going back that we just found is 0.99379, the area of that small section would be 1 minus 0.99379, which is equal to 0.00721. I'm sorry, 0.00621. 0.00621. All right. So at this point, we take our 0.99379 and we subtract this 0.00621 and we get 0.99379 minus 0.00621 and we get 0.98758. So again, this here represents everything going back from our 41 all the way out. But what we do is that we want to subtract as well at 31. We want to subtract this area back here. And it was quite conveniently given to us in this question that the z value for 31 was just equal to the negative of the z value for 41. So we were able to just subtract 1 from it to get the remainder of that area and subtract it again from what we've gotten, as the two areas are the same, to give us what is left back in this shaded region in the middle, the area or integral between 31 and 41, which is also the probability that our random variable x will lie between 31 and 41, which is 0.98758. However, our question did ask us for a percentage, and of course, it's trivial to find a percentage from a probability. This simply represents 98.758%. So, to answer the question at the beginning, which asked, at least what percentage of the computers will last between 31 and 41 months? Well, the answer is at least 98.758% of those computers, which is quite a lot.